Hello, and welcome to the next collection of recording sessions for the Probability and Statistics course for engineers and applied scientists. This is the launch point that moves us. We're still going to develop some additional ideas regarding the probability. So far, we've been talking about basic probability concepts. We looked at random variables and what is a probability distribution function. We looked at some common ones for discrete and continuous random variables. And now we're kind of in a segue point, and these recording sessions will be a mishmash of topics that I've just lumped under Introduction to Sampling. They do build off of what we've covered so far. Joint probability distributions, that's what this recording session will focus on. From there, we'll go into sampling basics, some descriptive statistics that people, that are commonly associated with sampling, and then something called sampling distributions. Again, your foundation, what we study so far in probability distribution functions will be be used here in these sections. So, joint probability distributions, we've so far focused all of our attention on just a single random variable, and what is the probability distribution function for that random variable taking different values. And so we assign probabilities to them, and sometimes they were discrete random variables, sometimes they were continuous random variables, but it was always one random variable that we looked at. Now we turn our attention to something called the joint probability distribution, which is the joint behavior of two random variables. This gives the example of joint behavior of life length and the casing strength of batteries. And so let me just go right into a table. Most of what I talk about now will be on the bivariate, just two variables, but this goes much broader into the multivariate distributions as well. But let's start off with a bivariate. I like, as you know from class, I'm very visual. I like numbers. I like to get in and have these kind of examples. So let's look at it through an example. Here's the National Highway Traffic Safety, interested in the effect of seatbelt use on saving lives. One study focused on children under the age of 5 who were in motor vehicle accidents in which at least one fatality was involved. Study showed, and this is actual live data from 1991 from the National Transportation Board, or can't remember the reference anymore actually, but it was truly a study. They looked at 7,060 accidents between 1985 and 1989. As you see, one variable, X1, looked at the survivability. So if a child survived, the random variable had a 0 assigned to it. If the child did not survive, the random variable took a value of 1. Then they looked at the seatbelt status associated with each of those children, and X2 tracked if no belt was worn, the random variable took a value of 0. If an adult seatbelt was used, the random variable X2 took a value of 1. And if the child car seat was used, then the random variable X2 would take a value of 2. And so these are the actual, you could imagine looking back at 7,060 records, data points, and just doing a cross match between, okay, did the child survive or not? And were they wearing no belt? So if they were survivors and they didn't have a belt, there were 1,129 of those. Total number of, out of these 7,060, 1,638 were children who did not have any belt, and so forth. So it's just a basic set of data here, right? So what is a joint probability distribution function associated with X1 and X2? And that is looking and saying, okay, X1 takes the value of 0 and 1. Again, 0 if they survive, and 1 if they do not. And X2 was tracking no belt adult belt or children's car seat belt. And so that's the 0, 1, 2 values. So it's a mapping of something that's non-quantitative into a random variable, two random variables in this case that do take numbers to them and associate to those different attributes. So this is the probability distribution function of those two random variables. As you see in the blue, 0.24, basically all it was doing is from the top table, you see 733 children who had survived and were wearing a children's car seat belt. Then that translates to a probability that the random variable x1 will be 0 and the random variable x2 will have a value of 2. That probability was 0.24, calculated by taking 733, which you see in the top table, divided by the total number of children, basically, who were studied, who were as part of this study. That, again, it goes back to the 7,060 accidents, but 3,015 children evidently involved in this study. And so what you see here, general probability distribution function, probability x1, the random variable x1, taking a specific value, little x1, and x2, random variable, taking a specific value, little x2, has associated with it a probability of x1 and x2. Okay, so this gives you the joint probability distribution associated with these two random variables based on the raw data. We say that the marginal distribution would be looking and saying, okay, for it's a bit easier just to say it. So looking across one of these random variables and saying, okay, the marginal distribution for x2 is equal to 2. That is 0.29. And there you have the marginal distribution. And that is just going back to the raw data, that's 872. And divided by the total number of kids involved, which was the 3,015. Another term which takes us back to when we were looking at conditional probabilities. Similar kind of concept here. In general, conditional probability distribution fixes one value for one of the random variables. And for example, suppose that, let me go right to the numbers here. Probability that x1 is equal to 0 given x2 is equal to 0. That should ring a bell. Well, that was equal to the probability that in this domain of two random variables, that's equal to the probability that x1 is equal to 0 and x2 is equal to 0 divided by the probability that x2 is equal to 0. And so what we have here is it's similar to what we were doing with the conditional probabilities that I presented in previous recording sessions and that we've talked through in class, where we're saying, okay, probability that x1 is equal to 0 given x2 is equal to 0. So you're basically forgetting the other probabilities, the x2 equal to 1 and x2 equal to 2. You focus just on x2 equal to 0. And so we take the 0.38 and we divide it by the 0.55. So the conditional probability turns out to be 0.69. Conditional probability of x1 equal to 1 given x2 is equal to 0. Probability of x1 equal to 1 given x2 is equal to 0. That's going to be 0.17 divided by 0.55. Probability of x1 equal to 0 given x2 is equal to 2. Looking at the numbers, so we're going to have probability of x1 equal to 0, 0.24 divided by 0.29. That again, so the second question, what's the probability x1 equal to 0 given x2 is equal to 2? We look just at that third row there. We say that's equal to 0.24. That 0.24 translates to the probability that x1 is equal to 0 and x2 takes the value of 2. So 0.24 divided by 0.29 is the conditional probability that x1 takes value of 0 given x2 is equal to 2. Okay, so we have learning checkpoint here. Associated with this, 2 construction contracts are to be randomly assigned to one or more of 3 firms. Numbering the firms 1, 2, and 3, let x1 be the number of contracts assigned to firm 1, and let x2 be the number assigned to firm 2. A firm may receive more than one contract. Find the joint probability distribution for x1, number of contracts assigned to firm 1, and to x2, the number of contracts assigned to firm 2. Find the marginal probability distribution for x1, and then find the conditional probability. What's the probability that firm 1 receives one contract given that x2 has already received one contract out of the 2? Okay. So as before, you have the solutions out there on the blackboard that you can retrieve. Just try it out, check them out. Independent random variables. So 2 events, A and B, are independent if A and B, probability of A and B is equal to the product of A and B. That should sound familiar from what we've talked about before. In this area, we say 2 random variables, x1 and x2, are said to be independent if, for basically you want to say similar to above, probability that the random variable x1 takes a specific value, little x1, and x2 takes a particular value, x2, that is equal to the product. That particular pairing of values of x1 and x2, taking those particular values, that has to be equal to the product of x1, probability of x1 equaling that specific value x1, times the probability that x2 takes the value of little x2. And you do that for all combinations of what x1 can, all real numbers, x1 and x2, that your random variables x1 and x2 can take. So that's that's your checkpoint. Are these 2 random variables independent? Well, if all of those pairings, if the joint probability turns out to be the product of those 2 of the marginal distributions, then you have independence of the random variables. Something to practice on with this point would be go back to the joint probability distribution function provided by the National Transportation Safety example on slide 5, and were those statistically independent? Similarly, you could do it for the learning checkpoint example. Give that a try. See whether there's independence or not. So again, just a brief look into joint probability distribution. This is again just focused on the bivariate discrete probability. The same general concepts extend to bivariate continuous. Now this was this is all from the standpoint of discrete probability distributions. You could do the same thing with continuous distributions. Similarly, you take this kind of intuitive, hopefully initial conceptual look into bivariate, and you could look at it from the same standpoint and say, okay, instead of x1 and x2 and a joint probability distribution associated with just those 2 random variables, you could have x1, x2, x3, and look at a joint distribution, probability distribution function associated with those 3 random variables, or k random variables, and have multivariate distribution associated with all k random variables. So, and again, I refer you to your textbook for additional information on this. The sections of the textbook are outlined in the blackboard for further reference. And this is just a first brush at that. I'll now conclude this recording session, and the next one we'll pick up with sampling, the introduction to sampling, and descriptive techniques, descriptive statistics.